Hello, in this video I want to calculate this expression for the kinetic energy of a rigid body. So I will consider it a rigid body and I will consider a differential mass in the rigid body dm. We know that the kinetic energy for a particle for a small mass is equal to half times that mass dm times the magnitude of the velocity of that differential mass squared. So if I want to find the kinetic energy of the whole rigid body, I'll have to integrate the kinetic energies of the differential masses composing the rigid body. So T of the whole rigid body is the integral over the body of half V dot V dm. And remember, I can write dm as rho dV, dV being the volume of the differential element. dm is the mass of the differential element. Rho is the density, and if the body is uniform, has uniform density, then rho is constant throughout the body. Okay, so now I want to introduce the center of mass in this expression because it pops up in the general expression for the kinetic energy. So I can relate the velocity of any point on the body to the velocity of the center of mass. This is my center of mass C, and I can write that V minus Vc. So V is the velocity of the differential mass dm. V minus Vc is equal to omega, the angular velocity of the body, plus r minus rc. For convenience, I'm going to denote r minus rc as pi. That's just the position vector of the differential mass relative to the center of mass of the body, lowercase pi. And the angular velocity of the body is equal to, in general, omega x ex plus omega y ey plus omega z ez. Later on, we will simplify the expression of the kinetic energy, taking into account that in this course, we only consider the angular velocity to be along ez, so that omega x and omega y are 0. But let's not do that just yet. So going back to our expression for the kinetic energy, integrating over the body, half, that's a constant I can take outside the integral. V, now I can write V as Vc plus, no need the brackets here, parentheses are enough, plus omega cross pi dotted with Vc plus omega cross pi dm. Okay, now I can simplify these expressions. That's half the integral over the body of Vc dot Vc dm plus the integral over the body 2 times Vc dot omega cross pi dm plus the integral over the body of omega cross pi dotted with omega cross pi dm. And let us now simplify these expressions to hopefully get the expression for the kinetic energy that we want, the one on the top of the page here. Okay. Right, so let's start with the first integral. The integral over the body of Vc dot Vc dm. Now, the velocity vector Vc of the center of mass does not explicitly depend on the particular differential mass dm we're looking at, or differential element we're looking at. So I can take those outside the integral, and that's just the integral over the body of dm. So this first integral simplifies to just the total mass of the body. That's the integral of dm over the whole body times Vc dot Vc. Awesome. So I think right now we've recovered this first term. The other two expressions should yield the other one. So let's continue. Now I'll look at this integral here. The integral of Vc dotted with omega cross pi. Okay, awesome. So here Vc and omega also do not depend on the specific differential mass we're considering. So these are constants that I can take outside the integral. Vc dot omega and then crossed with the integral of over the body of pi dm That's taking VC and omega outside, not changing the order of the operations at all. But remember this integral of pi dm, that's just equal to 0. That's because that's the integral, remember, of r minus rc dm. And the integral of r dm is just rc times the total mass, and the integral of rc dm is rc times the total mass. So this is equal to 0. So that whole integral goes away. That's equal to 0. Now let's look at the third integral over here. Okay, this one is a little bit strange looking. Let us see. The integral over the body of omega cross pi plus or dotted with omega cross pi. Okay. To simplify this one, we'll need to use an identity from math. Let me pull it up because I always forget these identities. Yes, it's this one. A cross B dotted with C cross D, that's equal to A dot C times B dot D minus A dot D B dot C. Okay, so then in this particular case, that integral becomes the integral over, okay, A cross B, that's going to become A dot C. So omega dot omega and B dot T, that's pi dot pi, pi dot pi, minus omega dot pi, omega dot pi. Cool. dm. Okay. Furthermore, this simplifies to pi. I will take the dot omega as a common factor, and I'll get pi dot pi along omega minus omega dot pi along pi dotted with omega. So these two expressions are the same dm. And now I can take omega outside the integral. That's the integral over the body of pi dot pi omega minus omega dot pi dm dotted with omega. And this integral over here should be familiar. That's hc, the angular momentum above the center of mass. So finally I'll get that hc dot omega is equal to this integral. Awesome. So that's equal to hc dot omega, the blue integral. So now if I take back all these results and plug them back into the expression of the kinetic energy, T is equal to half the red result, that's half m Vc dot Vc plus the red, the pink integral is 0. The green one is half Hc dot omega. Awesome. And I know that if omega is just along EZ, then Hc is gonna be equal to Ixc, the product of inertia, Ixc about C omega Ex plus Ic Yz omega Ey plus Ic Zz omega Az. And dotting that with omega, which is just along Ez, I'll get that if omega is just along Ez, that half Hc dot omega is equal to half Ic Zz omega squared. Okay, so that's it. We showed this expression.